Hello everyone, thanks for coming to this talk. I am Hao Chen from Ant Group. Today I'm going to share our experience with adopting Ray and improving Ray for our large-scale applications in production. First, a little bit introduction about myself. I joined Ant in 2018 and started working on Ray since that. Now I'm leading the Ant Recall team. We focus on improving Ray and supporting other teams to build their applications and frameworks on top of Ray. We also work closely with the open source community and have contributed a lot of improvements to the open source Ray. And then let's take a look at what we have built on top of Ray. In the first 2 years, we have been focusing on three major projects. The first one is a real-time graph computing system. With this system, we can bridge graph computing together with stream computing. And we are using it for a wide range of scenarios. For example, fraud detection, data lineage analysis, graph-based machine learning, and so on. The second one is an online machine learning system. With this system, we were able for the first time to run the whole online machine learning pipeline in a single system. And this, in turn, improved the end-to-end efficiency greatly. And now we are using it to build a lot of recommendation and ad systems for the Alipay app. The third one is called Online Computing Service. With this system, we can allow users to do distributed computations on online services. And we use it to build online services that can do complex financial decisions. And last year, we started a new project that is using Ray for distributed operational research. With this system, we can allow users to quickly develop high performance and robust distributed operational research algorithms. One use case of this system is to resolve the online resource allocation problems. And this year, the most important new project that we are focusing on is a large-scale Python data processing project. This is a collaboration project with the Moss team. Moss is also an open source project that scales your NumPy, Pandas, or scikit-learn code. And besides the above, we also have some ad hoc distributed systems built in on Ray. And in the past 3 or 4 years, we have built a lot of systems on top of Ray, and they span across different technical or application areas. And our ultimate goal is to use Ray as a universal foundation for all kinds of distributed systems. With the previous applications, our total scale of Ray has been increasing rapidly. In the past 3 years, we have increased our total number of CPU cores from 0 to more than 200,000. And in this talk, I'm going to talk about what problems and challenges we have met during this journey and how we solved them and improved Ray. Before diving into the concrete problems, let's take a moment to revisit what Ray architecture looked like back in 2018. So usually in a typical worker node, we have some driver and worker processes. And we have a relay process that can manage these workers. And we also have an object store that provides shared memory for these workers. And usually we have multiple such nodes in the cluster. And there's also a special head node in the cluster, which is called head node. The head node mainly consists of the GCS, which is implemented by a Redis server plus a Redis module. And okay, the first challenge I'm going to talk about is the performance of actor cores. As I mentioned before, one of the earliest projects we started working on Ray is the online machine learning system. In this system, the stream data processing is a key component of it. And to implement a streaming library with Ray is straightforward. We can simply use Rearchitecture to implement the streaming workers. And the stream workers will continuously send messages to the other workers by actor calls. So we can see the performance of the actor calls is critical in this system. However, in the old versions, the performance could not meet our requirement. Let me explain why. Let's say we have two nodes and two actors on each node. If actor 1 wants to send a message to actor 2, the message actually needs to go through both relays on the two nodes. And if we have multiple such pairs, the relay can easily become the bottleneck. We resolve this problem with a new architecture that we called direct actor calls. We removed relays from the critical path and let the actor talk to each other directly through gRPC. And the callers can get the location of the callees by a Redis pub/sub channel. And because the new RPC layer is implemented in C++, it's highly efficient. This is a benchmark I did on an average Linux machine. We can see with direct actor calls, we increased the actor call throughput by 6x. And also, after we contributed actor calls to the open source Ray, normal tasks were also switched to direct calls by the community. So now everything in Ray is direct. And besides direct calls, we have also done a lot of improvements in the RPC layer in order to further optimize the RPC performance. We profile the program and optimize the hot code path. For example, we reduced copies, we added caches, and we use dedicated I/O threads, and so on. With these optimizations, our latest Ray has achieved 10x throughput compared with Ray 0.8.2. So the next challenge I'm going to talk about is actor failure recovery. In the graph computing system, we use a simple but useful mechanism to handle failures. That is, if any actor fails in the system, we will kill and restart all the other actors. So this system has a strong requirement on the speed and reliability of Ray's actor failure recovery. And in old versions, actors were managed by multiple relays simultaneously. Let me explain what the problem was with that. So let's say we have 3 nodes in the cluster and 1 actor on the first node. Then for some reason, the node 1 goes down. At this time, the other 2 relays will try to restart the actor. They will first try to acquire a list from the Redis. Let's say relay 3 gets the list. And now relay 3 is responsible for creating the actor. And it should also update the list within a timeout before the actor creation finishes. And then if something wrong happens in the network and relay 3 fails to update the list, relay 2 will think relay 3 is dead, and it will get the list again and create the actor again on its local node. So the problem is that we end up with multiple duplicated actors. This problem is severe for large clusters or when the network condition is bad. To work around this, we have to sacrifice the actor restart speed by setting longer timeouts. The root problem here is that actors are managed by multiple relays in a distributed way, and it's hard to avoid inconsistency among these relays. But considering that the number of actors in a cluster is usually limited, so it makes more sense to manage these actors in a centralized way. And GCS is the perfect role to do that. However, it was not easy to do that with the old architecture. As I mentioned before, the old GCS was literally implemented by a Redis server and a customer Redis module. So this means that the API was constrained to only Redis commands, and it was hard to implement complex logics within a Redis module. And also, it was also hard to ensure fault tolerance of GCS with the old architecture. We resolved this problem with a new architecture that we called GCS Service. We replaced the old GCS with two new components, a RPC service and a pluggable storage. Now with this new architecture, we re-implemented actor management in GCS, and now we can ensure that actor failure recovery can always succeed. And we have also optimized the speed. Now it only usually takes 1.5 seconds to restart one actor or 70 seconds to restart 10,000 actors. And also based on this new architecture, we implemented GCS fault tolerance. We just store the states of GCS in a persistent storage, and the GCS service can simply restore and recover the states from the storage in case of failure. Besides actor management, other features have also benefited from the new architecture. For example, cluster membership management, job management, and placement groups are also implemented based on the new GCS service architecture. And internally at Ant, we have also implemented a new actor scheduler based on GCS. Because GCS has the global view of the cluster resources, so it can make more precise decisions, scheduling decisions. This feature is not open source yet. We are working on open sourcing it. So in these slides, I will use this small icon to indicate such features. After we resolved the previous problems, we were able to run our applications with medium or with small or medium scales. And but as our scale continued to increase, reliability and scalability became the new challenge. For example, with larger scale, we were more likely to see failures that were caused by environmental errors or edge case bugs. And also, as our applications got more complex, we needed to use larger clusters to support them, and the increased workloads also made Ray flakier than before. Another challenge was that as we have more and more clusters, it becomes hard to manage these clusters. Let's talk about the first question first. How can we make our applications fault tolerant to these occasional errors? First of all, we need to make sure that every component in the RAID system is fault tolerant. For GCS, we already mentioned that we solved this problem with the new GCS architecture, GCS service architecture. And for relays, we deploy a daemon process on each node, which monitor and restart the relay in case of failure. And to handle node failures, our Kubernetes operator will replenish the cluster with the new nodes. And besides fault tolerance in the system layer, we also want to make it easy for the users to write fault-tolerant applications with Ray. So for the tasks and actors, they come with convenient API that can allow you to automatically retry or restart them. And for placement groups, we implemented this feature with automatic failure recovery, so users don't have to be aware of this at all. And internally, we have also implemented some libraries to help users to deal with some common failure patterns. And one example is to fate share multiple actors. And lastly, to prevent regressions, we also set up automatic fault injection tests that runs every day. The second question is how we can support more workloads in a single cluster. We did a lot of optimizations in our code to increase the scalability of the cluster. For example, we separated the heartbeat messages and the resource update messages. We reduced the sizes of the pub/sub and the RPC messages. And we also reduced the number of connections between different components in the system. And for Java applications, we have also implemented a new feature that allows users to share multiple actors in one single JVM process in order to reduce the memory overheads. With these efforts, we are able to support more than 1,000 nodes and 10,000 actors in a single cluster. And the third question I mentioned before is how to manage the whole deployment. Previously, we would create a new cluster for each job. This led to too many clusters, and they became hard to manage. And also, since we needed to initialize the cluster before starting a job, the job startup time was slow. And another drawback was that it prevented us from further optimizing the resource utilization across different jobs and applications. In order to solve these problems, and now we are migrating to the new multi-tenancy model. And to support multi-tenancy, we implemented job isolation in both process level and node level, and we introduced job level configuration. The last challenge I'm going to talk about is debugability and accessibility. So we all know that distributed systems are hard to development, and they are even harder to debug. Ray has simplified the development of distributed applications, and users don't have to know much about the underlying details. However, this also means that when something wrong happens, users also have no idea what the problem is. So we had to spend a lot of time helping users debug problems. This became unacceptable as our scale kept increasing. So the question is, how can we make Ray a self-service system? Last year, we put a lot of efforts on improving Ray's dashboard. We built a new dashboard internally. Now with the new dashboard, you can literally find all the information you need. For example, you can see the resource usages, the states of an actor or a node or a worker, the configuration of the cluster or for a particular job, and so on. And you can also see the logs, errors, and the key events on the dashboard. And based on these events and the logs data, we are also building a new tool that can automatically analyze some common problems. Last but not least, we have also integrated some common debugging tools with the dashboard. For example, you can view the stack of your running processes, or profile your processes, or analyze the memory of your processes directly on the dashboard. This new dashboard has been partially open sourced. If you want to give it a try, you can click this button on at the upper right corner of the old dashboard, and please let us know if you have any feedback. And besides the new dashboard, we have also simplified the process of job submission. And right now, users can simply submit their jobs from a web portal or RESTful API. and the users can simply specify the dependencies directly in the request, and the Ray will automatically download them into the cluster. And we have also implemented caches for some common dependency management tools in Python and Java. So usually a job only takes a few seconds to start if the cache is hit. And this internal feature has some overlaps with the runtime end feature in the open source Ray. And now we are working on integrating them and making the job submission also available to the open source users. At the end of my talk, I'm going to talk about a few things that we plan to focus on in this year. For scalability, we plan to support at least 5,000 nodes and 50,000 actors in a cluster. And regarding scheduling, we have seen some new challenges because we are running mixed workloads from different applications and jobs in a single large cluster. So we plan to improve the performance and the resource utilization of the scheduler. We also plan to improve the auto-scaling feature of Ray. The next thing is to better support data-intensive applications. So more precisely, we plan to improve Ray's object store and support running masks on Ray. And we also plan to implement some advanced features and some common libraries. For example, we plan to implement a library that can allow users to monitor their actor states in their application code. And we also plan to support more sophisticated threading model. For example, some users may want to run their different actor methods in different threads. Last but not least, we also plan to enhance the C++ worker and support a few applications in production. Okay, thanks. That's everything from my talk. Thanks for your time. Hope you enjoy it. Please let me know if you have any questions. I will be available during the Q&A session. Thank you. See you there.